Now we're going to move on to another coordinate system, that is spherical coordinate system. So for spherical coordinate system, spherical coordinates make it simple to describe a sphere. In the spherical coordinate system, the point P in space is represented by the order triple of the form rho, theta, and phi. So here, this is pronounced as rho, this is theta, and this notation is phi. Now the descriptions for each component in the order triple written in spherical coordinate system is, so rho is the distance from the point P to the origins. Distance from the point P to the origins. Theta is the rotations from the positive x-axis and the bound for theta is between 0 and 2 pi. And theta, this theta is similar to the theta described in polar coordinate system and cylindrical coordinate system. And phi in this case is the rotations from the positive z-axis. And the bound for phi is between 0 and pi. So the point that we have here, rho, theta, and phi, can be visualized using the following figure. So the point of consideration is the point in this form, x, y, and z, and you would like to convert this point to the point of the form rho, theta, and phi. For rho, again, is the distance between the origins and the point of considerations, in this case, the point P. Theta is the rotations from the positive x-axis to the line segment connecting the point projected on the xy plane and the origins. And you remember from the polar coordinate system and the cylindrical coordinate system, the line segment connecting the origins and the point on the xy plane is equal to r. And phi in this case is going to be the rotations from the positive z-axis to the line segment connecting the point and the origins. Now the next thing that we're going to do is we're going to derive a set of equations that help us convert from a rectangular coordinate system to a spherical coordinate system and vice versa. Now what we're going to do is that we're going to look at this particular triangle. Okay. And we're going to zoom into this particular triangle and put it out here to work with. A few things that I want to mention. So here, the line segment connecting the origins and the point on the xy plane has the distance of r. And this distance is going to be the same with this distance. So this one is also r as well because they are parallel to one another and they are equal to one another. And because z is going to be orthogonal to any vector on the xy plane, it's going to perpendicular or orthogonal to this line segment r. And because these two lines are parallel to one another, therefore this line r is going to be perpendicular or orthogonal to the z-axis as well. Alright, so when you zoom into this particular triangle and bring it out here to work with, this is the right angle that we're looking at compared between the two figures. And this is the angle phi. Next, we see that for this side of the right triangle, the length of the side is equal to r. So this is r. And for this side of the right triangle is the z value. So we have this is equal to z. From here, we're going to derive a set of formula to connect spherical coordinate with rectangular coordinates. So that is, we're going to look at cosine of phi and sine of phi. So cosine of phi is going to be the adjacent, which is z in this case, over the hypotenuse, which is rho. And from here, you can solve for z, which is equal to rho times cosine of phi. Now for sine of phi, we have the opposite over the hypotenuse. So the side that is opposite of phi is r. So you have r over rho. And this is equivalent to writing r equal to rho times sine of phi. But from the cylindrical coordinate system, we have that. But from the cylindrical coordinates, we have that r now equal to rho times sine of phi. But if you multiply both sides of this equation for cosine of theta, what we're going to achieve is an equation of the form. So on the left hand side of the equation is going to be equal to x because x is equal to r times cosine of theta. So in this case, x is equal to rho times cosine of theta times sine of phi. Similarly, if we're going to start with this equation, r equal to rho times sine of phi, and we're going to multiply both sides of the equation by sine of theta, we're going to get that y is equal to rho times psi of theta times psi of phi. And one more equation here, that is z equal to rho times cosine of phi. So you have z equal to rho times cosine of phi. So this set of equations going to help us convert from spherical coordinate system to rectangular coordinate system. What you're going to do next is you're going to find a set of equations that help us convert from the rectangular coordinate system to spherical coordinate system. What we're going to do with this three equation is that for each equation, you're going to square both sides of the equations and add them up together. So that is, if you have x squared plus y squared plus z squared, you're going to get rho squared times cosine squared of theta times sine squared of phi plus rho squared times sine squared of theta times sine squared of phi plus rho squared times cosine squared of phi. Now, for each term on the right-hand side, you have rho squared as a common factor, so you factor it out, and you left with cosine squared theta times sine squared phi plus sine squared theta times sine squared phi plus cosine squared phi. Now, for the expressions inside the parentheses, you notice that sine squared phi is the common factor for the first two terms, so we're going to get rho squared times sine squared phi times cosine squared theta plus sine squared of theta plus cosine squared phi. For cosine squared theta plus sine squared theta, that's going to be equal to 1 because that's the trigonometric identity. And you left with rho squared times sine squared phi plus cosine squared phi. And again, what we have here is equal to 1, which is a trig identity. Therefore, you obtain x squared plus y squared plus z squared equal to rho squared, or rho is going to be equal to square root of x squared plus y squared plus z squared. So these equations we just derived allow us to convert from one coordinate system to another coordinate system. In particular, using this equation, we can convert the point from a spherical coordinate system to rectangular coordinate system. And if we use this information, we can actually convert a point from the rectangular coordinate system to spherical coordinate system. Now let's take a look at the following example. I would like to express the point 8 pi over 3 pi over 6 into the rectangular coordinates. So the point that is given to us is in spherical coordinates. That is, this is equal to rho, this is theta, this is phi. One thing I would like to point out to you that we are in context of mathematics, and therefore the point in spherical coordinate is written in the order of rho, theta, and phi. In physics, sometimes you actually swap the positions of phi and theta, so you have to be careful with that, and I want to point out that to you in the context when you read the textbook and you see the order of theta and the phi get swapped around. That is not incorrect, that is just the way that the problem presents. One is in mathematics context and the other one in physics context. So in this case, you have the order of rho, theta, and phi. Now I want to convert this into the rectangular coordinate of the form x, y, and z. For x is equal to rho times cosine of theta times psi of phi. Y is equal to rho times psi of theta times psi of phi. And z is equal to rho times cosine of phi. For rho is equal to 8, theta is equal to pi over 3, and phi is equal to pi over 6. So you have rho to be 8 times cosine of pi over 3 times sine of pi over 6. This is equal to 8 times cosine of pi over 3 is 1/2, and sine of pi over 6 is also 1/2. So you have 2 for the answer. For the y component, you have 8 times sine of pi over 3 times sine of pi over 6. So this gives you 8 times root 3 over 2 times 1/2, or this is 2 times root 3. And for the last component, z is equal to rho times cosine of phi, or this is 8 times cosine of pi over 6, or 8 times root 3 over 2. Or this is going to give you 4 times root 3. So the point in a rectangular coordinate is of the form 2, 2 times root 3, 4 times root 3. So that is the procedure to convert from the point in spherical coordinate to the point in rectangular coordinate. Now I'm going to move on to the next example. In example 5, we want to convert the rectangular coordinates of -1, 1 and square root of 6 to both spherical and cylindrical coordinates. So I'm going to do this for cylindrical coordinates first and then convert that to spherical coordinates. So the point given to us is in rectangular coordinate form. So you have x, y, and z, and you want to convert to cylindrical coordinate of the form are theta and z, and also you want to convert this into spherical coordinate of rho, theta, and phi. So these two theta here that you see in cylindrical coordinate and in spherical coordinate are the same. So if you can calculate theta for one set, then you can apply that for the other set. First, you want to convert from rectangular to cylindrical. So to do that, what you need is r is equal to square root of x squared plus y squared. This is equal to square root of -1 squared plus 1 squared. This is root 2. For theta, I'm going to use tangent of theta equal to y over x. This is going to give you 1 over -1. This is equal to -1. So x is negative and y is positive so the point x comma y is in the second quadrant of the xy plane. Therefore, theta in that case is going to be equal to 3 pi over 4. And the z value is equal to square root of 6. So the point from -1, 1 root 6 to the point in cylindrical coordinate and has the form root 2 comma 3 pi over 4 comma square root of 6. Now from here, we're going to do rectangular coordinate to spherical coordinate. We're going to need the point of the form rho, theta, and phi. So for rho, we're going to get rho equal to square root of x squared plus y squared plus z squared. Well, this is equal to -1 squared plus 1 squared plus root 6 squared. Or you're going to have 2 plus 6, or this is root 8, or you can do 2 times root 2. Now theta, as I mentioned earlier, the theta in cylindrical coordinate and the theta in spherical coordinate are the same. Therefore, theta is already found in this part, so theta is equal to 3 pi over 4. For phi, I'm going to use the equations cosine of phi is equal to z divided by rho. For z is equal to square root of 6 and rho is equal to 2 times root 2. And you simplify these fractions, you're going to get root 3 over 2. Remember when we first talked about rho, theta, and phi, we restrict theta between 0 and 2 pi, and we restrict phi between 0 and pi. So therefore, when cosine of phi is equal to square root of 3 over 2, we get that phi is equal to pi over 6. Therefore, the point -1, 1, square root of 6, written in spherical coordinate system has the form of 2 times root 2, comma 3 pi over 4, comma pi over 6. Now we're going to move on to the next set of example. That is, you are given an equations in a spherical coordinate. You want to convert that into rectangular coordinate system. So in this case, you have rho equal to 3. We can relate rho back to rectangular coordinate system through the equations of the form square root of x squared plus y squared plus z squared. This is equal to 3. Or if you square both sides of the equation, you get this is x squared plus y squared plus z squared equal to 9. So this is a sphere. Center at the origin with a radius 3. Now in the next equation, you get rho equal to 2 times cosine of phi. Again, the idea is to convert this equations from spherical coordinate system to rectangular coordinate system. What you notice is that on the right hand side, you can get z by making rho appear on the right hand side. To make rho appear on the right hand side, what you can do is you multiply both sides of the equation for rho. So you have rho squared equal to 2 rho times cosine of phi. On the left hand side, you have x squared plus y squared plus z squared. And on the right hand side, it's just z. So this equation we just got is the equation in rectangular coordinate system. Now for c, you have rho equal to 4 times cosecant of phi. And before we do any conversions, let's start rewriting cosecant of phi in terms of 1 over sine of phi. So that is 4 times 1 over sine of phi. And sine of phi is written as r over rho. So you get 4 over r over rho. You divide a fraction, that means you can multiply by the reciprocal, so you have 4 times rho divided by r. Now the equation is of the form rho times 4 rho over r. You see that rho can be eliminated on both sides of the equations, or you get 1 equal to 4 over r, or r is equal to 4. So technically, you can relate r back to the rectangular coordinate system through the equations of r equal to square root of x squared plus y squared. So the equation becomes square root of x squared plus y squared equal to 4, or you get x squared plus y squared equal to 16. So what you have here is the circle on the xy plane with radius 4, center at the origins. So this is the circle on the xy plane, center at the origins, with radius 4. So technically that's it for me. So in this case, we learned how to convert from one coordinate system to another coordinate system. More specifically, we derive formula to convert points or equations from cylindrical coordinates to rectangular coordinate system and vice versa, as well as converting points and equations from the spherical coordinate system to rectangular coordinate system. So that's it for me. Please let me know if you have any questions. Thank you.